Hello everyone, welcome to the YouTube channel of Yourpedia and Engineering Point. So I am Vinesh Sharma, your mentor of mechanical engineering. So as you know, the BEL, BDL as well as the BHL has announced the vacancies for mechanical engineering, and we have already started the various module to prepare those exams here. Okay, so you can join those module and just continue your preparation. So if you remember, in the last video we have covered some basic practice question related to the IC engine, which is a part of applied thermodynamics, and in this video I am going to cover up the next part, that is power plant engineering here. Okay, so if you see, if I talk about the syllabus of the basic thermodynamics and the applied thermodynamics, the syllabus is very simple. You should have a basic understanding of the basic thermodynamics first of all. Okay, and in the case of applied thermodynamics, you should have a basic understanding of all these practical cycles which we carry out into in our day-to-day applications here in the industries. Okay, and along with that we should have a basic knowledge of the various practical devices which you find in the industries here. Okay, so that is required for the applied thermodynamics only. So now let us start with our questions here. So if you see, in the first question what is being asked, that I consider the simple ideal Rankine cycle with fixed boiler and condenser pressure. If the steam is superheated to a higher temperature, which one is the correct option here then? Okay, so you have to mark the correct option out of these four options here. So here we are talking about the Rankine cycle. See, Rankine cycle is a practical cycle for this thermal power plant or a steam power plant here, and in the case of Rankine cycle we have four processes. These four processes are isobaric heat addition and heat rejection process. Then we have a isentropic compression and expansion process here. Okay, so if you see, just see, remember, if I just simply draw the TS diagram of Rankine cycle, it can be shown something like that. Okay, so this TS diagram is representing the Rankine cycle with the superheating of the steam in the boiler, and if I show you the simple Rankine cycle without superheating. Okay, so this red color cycle is representing the Rankine cycle without superheating here. So now what we have to do, we have to compare this simple Rankine cycle with the cycle with superheating here. Okay, so in the case of simple Rankine cycle, you can see the expansion of the turbine, expansion of the steam is taking place from 1 to 2. Okay, and it is inside the dome, and whereas as you are doing this superheating from 1 to 1 dash to 2 dash, the corresponding superheating is being done here. Okay, so let us compare these two cycles. So the first option is the turbine work output will decrease. So if you compare the simple Rankine cycle with the superheated Rankine cycle, here we can simply say that the work output from the turbine is going to be increased. Okay, because the enthalpy change between the 1 and 2 is going to be more in the case of superheated region as compared to the wet region here. Okay, so therefore we can say the option number A is incorrect here. The second part is the amount of heat rejected will decrease. Okay, so just see, in the case of a superheating, in case of whenever you are doing the superheating, the corresponding heat rejection is represented by the 2 dash to 3 here. Okay, and initially it is from 2 to 3, so we can say the heat rejection from the condenser is also being increased here. Okay, that means the option number B is also incorrect. The next part is cycle efficiency will increase. See, in order to compare the cycle efficiency, you should have a basic understanding that by doing the superheating, reheating or regeneration, whatever you are doing, what is the effect of the effect on the mean temperature of heat addition and mean temperature of heat rejection. Okay, because if I just write down the efficiency formula in terms of mean temperatures here, so it can be written as this one here. So where the TMR is representing the mean temperature of heat rejection and MA is representing the mean temperature of heat addition here. Okay, so as soon as you are increasing the mean temperature of heat addition due to this superheating, the corresponding efficiency is also going to be increased. Okay, so we can say the option number C is going to be the correct one here. The next part, the moisture content at the turbine exit will decrease. That is also wrong, because the moisture content at the turbine exit will decrease. Yeah, that is also correct. Why so? Because if you see in this case, at point number 2 we have a higher amount of moisture content because the dryness fraction value is very less here. So as soon as you are doing this superheating, the corresponding 2 dash state is at a saturated vapor state here. Okay, so we can say the dryness fraction is going to be increased and the corresponding moisture content is also going to be decreased. So here in this question, option number C and option number D both are basically correct here. Okay, so that is the very simple part. Next part, the Rankine power cycle is idealized. Which one of the following is not one of the idealization here? So basically in this case, it is asking you to find out that which one is not the assumption of the Rankine cycle here. So first one is the friction is absent. That is basically a correct here. Okay, because the friction is always we always consider that the friction is not present. in all the processes. That is why the cycle is considered as a internal reversible cycle here. Next part, the heat transfer does not occur across a finite temperature difference. That is a wrong statement, because in the case of Carnot cycle only, the heat transfer is taking place through a zero finite temperature gradient. But in all the other cycles, whenever you are studying the Otto cycle, diesel cycle, Rankine cycle, Brayton cycle, in all of those cycles, the heat is being transferred through a at a constant pressure process, or whether it is transferring at a constant volume process. So we can say the heat transfer is basically occurring across a finite temperature difference here. Okay, so here the option number B is going to be the correct answer here, because in the case of Rankine cycle, actually the heat is being transferred at a constant pressure process. Okay, and at the constant pressure process there is a finite temperature difference. So that is why the option number B is incorrect here. Next, pressure drop in pipe is neglected. Yes, that is also correct here. The pipe connecting components are insulated. That is also correct. That is why the heat loss is not taking place from any of the components here. Okay. The next part, steam enters a diffuser at a Mach number 2.5 and exit at Mach number 1.8. What will be the shape of diffuser? So first of all, just say in this question, what is entering a diffuser here? So steam is entering a diffuser, and steam is considered as a compressible flow. Okay, and now if you see, the Mach number at the entry is 2.5 and the corresponding Mach number at the exit is 1.8. So that means the velocity, the kinetic energy of the steam is continuously decreasing here. Okay, and that is the main purpose of the diffuser only. So whenever we talk about the compressible flow, in that case the shape of the diffuser must be convergent type here. Okay, when the Mach number of the fluid is more than 1. So here you can see, in this case, when the fluid is entering at point number 1 with a Mach number of 2.5, so then in that case this converging section is going to be act as a diffuser here. So that means all of the kinetic energy is going to be converted into the pressure energy, and the corresponding value of Mach number at point number 2 you are going to see less than the 2.5 here. So we can say in this case the option number B is also incorrect here. Okay, so the answer of the question number 3 is going to be B here. The next part, the enthalpy of a steam entering a turbine is given as 3200 kilojoule per kg, and the enthalpy after the isentropic expansion is 2400 kilojoule, and the enthalpy at the end of the actual expansion is 2560 kilojoule. What is the turbine efficiency? See, in this case actually what is happening, this is the dome here. So if you see at point number 1, the steam is entering into the turbine. So here you can see the expansion of the steam isentropically will be represented by this 1 to 2 point here. But now in this case the expansion is not taking place isentropically. That is why we are going to have a higher efficiency as compared to 2 here. Okay, so what do you want to find out? You want to find out the value of the turbine efficiency. That means this question is being asking you to calculate the value of the isentropic efficiency of the turbine. So if you just calculate the value of the isentropic efficiency of the turbine, it will be equal to H1 minus H2 dash divided by H1 minus H2 here. Okay, and the corresponding value of H1 is given to you as 3200 minus H2 dash is given to you as 2560, and H2 is equal to 2400 here. Okay, so if you just solve this value, you will get the final value of the isentropic efficiency of the turbine here. So here if you solve this, you will get an answer of around 80% here. So option number A is going to be the correct answer of this, option number B is going to be the correct answer of this question here. Okay, so that is a very simple part. The next part is the major loss in a steam power plant take place in. See, actually in the case of steam power plant, we have basic 4 components. The first one is the boiler, then we have a turbine, then we have a condenser, and then we have a pump. And if you remember, in the case of boiler, we are supplying heat into the system. In the case of turbine, we are getting the work output from the system, and in the case of heat condenser, we are rejecting the heat into the atmosphere here. So we can say the major loss which is taking place in the case of steam power plant is taking place through the condenser here. Okay, so option number C is going to be the correct answer out of these 4 options here. Okay, so that is a very, very simple part here. Next part, in the most steam power plant, closed feed water heater are favored, but open feed water is heater is used. See, Actually what happens, the closed feed water and the open feed water heater is used to for the regeneration purpose in the steam power plant. Okay, and if you see that what is the meaning of regeneration process here, regeneration process is a process in which what you are doing, you are basically preheating the water here. Okay, so that you have to supply less amount of heat into the boiler, so that the heat supplied will decrease. Okay, and correspondingly the work output is going to be remain same. That means the net effect of the regeneration is to increase the efficiency of the plant here. Now we have two options, either we can use the closed feed water heater, but we can also use the open feed water heater. So in the case of open feed water heater, what we are doing, we are extracting the some part of steam from the turbine, okay, and the remaining part of the turbine of the steam is basically expanding through the turbine here. So after the expansion of the turbine, what we do, we combine the two types of steams here, okay, in a proper mixing chamber, and we have to make sure that the pressure of both of the fluid has to be remain same, otherwise to minimize the losses here. Okay, so here the open feed water heater also does perform a function of deaerator here. Okay, so deaeration process is also performed by the open feed water heater. So out of these four options, we can say open feed water heater is used to deaerate the feed water by removing the dissolved gases here. Okay, so option number D is going to be the correct answer of this question. Next part, radial blade in a centrifugal compressor offer. Okay, so now just remember, when we talk about the compressor, what is the main purpose of compressor? Compressor is used to increase the pressure as well as the temperature of the fluid. Okay, and in the case of power absorbing device, the main purpose is to increase the temperature, and in the case of power producing device, the main purpose is to increase the pressure here. Okay, so that is the main purpose here. So in the case of centrifugal compressors, just remember, centrifugal compressor works on the principle of the dynamic state here. Okay, what we do here, we supply the kinetic energy into the fluid, which get further converted into the pressure energy. So in this case, we use a different types of blade. We have a radial blade here, we have a forward blade, and then we have a backward blade here. Radial, forward, as well as the backward blade here. So here we can use three types of blade here. Now if I talk about the highest pressure ratio generated by all of these blades, so highest pressure ratio is always generated by the forward blade, and the minimum pressure ratio is always generated by the backward blade here. Okay, and the corresponding efficiency, if I talk about, or I can say the power requirement, so corresponding backward blades require the very less amount of power as compared to the forward blade, and the radial blade properties are always lying in between the backward and the forward blade here. Okay, so if you see what are the benefits here, actually the radial blades are very simple to generate, very simple to manufacture here. Okay, and the corresponding the amount of stresses which is produced over the blade cross section is very less in the case of radial blade, because it is a symmetrical type here. So it is having a less weight also, it is having a less blade stresses also, and in terms of manufacturing it is very simple to manufacture here. So we can say the option number D is going to be the correct option here. All these statements are correct here in this case. The next part is, a large clearance volume in the reciprocating compressor results in. See, now what is the effect of large clearance volume in the reciprocating compressor? If you remember, in the case of reciprocating compressors are those compressors which work on the principle of positive displacement here. Okay, now how does it operate? Basically in this case we reduce the volume, and due to the decrease in volume, the corresponding rise in pressure is observed here. Okay, so here we define a one parameter which is known as the volumetric efficiency, and the volumetric efficiency is defined as the actual volume flow rate of the fluid into the compressor to the theoretical piston displacement here, or I can say the piston swept volume here. So if you further simplify it, its formula can be written as m dot v1 divided by pi by 4 d square L multiplied by n by 60 multiplied by k here. Okay, so this is the formula of the volumetric efficiency here. And if you further simplify this formula, you can also rewrite the volumetric efficiency in terms of clearance ratio also. So here you can see in from this formula we can say the volumetric efficiency is basically a function of the clearance ratio, pressure ratio, as well as the polytropic index also. Okay, so now in this question we are basically increasing the clearance volume here. So with the increase in clearance volume, what will happen? See, the clearance ratio is defined as the clearance volume divided by swept volume. So as soon as you are increasing the clearance volume, the corresponding clearance ratio will increase, and with the increase in clearance ratio, the corresponding efficiency is going to be decrease here. Okay, and the decrease in the less amount of volumetric efficiency means that the volume flow rate, basically the volume flow rate, we can say the actual volume which is being entered into the reciprocating compressor is going to be very, very less here. So option number C is going to be the correct option here in this case here. Okay, so that is a very, very simple part. Next part, next question. For a two-stage reciprocating compressor with an idle intercooler, the suction pressure is 1.66 bar and correspondingly the delivery pressure is 60 bar here. What is the value of the idle intercooled pressure? So that's a very simple case. In this case, you can simply calculate the value of the intermediate pressure by taking the geometric mean of the higher as well as the lower pressure here. Okay, so here we have a higher pressure, here we have a lower pressure. So just put all the values and you will get your final answer. Okay, so just solve it, you will get your answer here, and the answer of this question will come out to be around 10 bar here. Okay, so we can say option number A is going to be the correct answer of this question. Next part, in a steam turbine, the enthalpy drop in the fixed blade and the moving blade are 48 kilojoule and 32 kilojoule, and you have to calculate the value of the degree of reaction. See, now what is the meaning of degree of reaction here? Degree of reaction is a very important terms in the case of hydraulic turbine as well as in the case of steam turbine. So when we talk about the hydraulic turbines, it tells you about the contribution of the pressure energy in the total amount of work produced here. Because in the case of reaction turbine, the work output is being produced due to the contribution of pressure energy as well as the kinetic energy here. But now what is the exact contribution of pressure energy is there, that can be calculated by the degree of reaction. So for example, if the value of the degree of reaction is coming out to be 0.4, so we can say the total contribution of the pressure energy is around 40% in the total work output here. Okay, that is you have to remember. And in the case of the steam turbine, we can define the degree of reaction as the enthalpy change, or we can say enthalpy drop which is taking place in the moving blade as compared to the total enthalpy drop which is taking place in the moving blade as well as the fixed blade here. So here you can see the degree of reaction in the case of steam turbine can be calculated as enthalpy drop in the moving blade divided by enthalpy drop in the moving blade plus fixed blade here. Okay, so that is how you can calculate the value of the degree of reaction. So here in this case, the degree of reaction can be calculated as 32 divided by 48 plus 32 here. Okay, so that is how you can calculate the value of degree of reaction. So here you can see how much option you are getting. You are getting the answer as 40% here. Okay, so that means 40% of the total enthalpy change is basically taking place in the moving blade, and the remaining 60% enthalpy change is taking place in the fixed blade here. Okay, so that is the option number A is going to be the answer of this question here. The next part is, in an axial flow compressor, air enters and leaves the stage axially if the wall component of the air leaving the rotor is half the mean peripheral velocity of the rotor blade. So here in this case, in the case of axial flow compressor, wall velocity at the exit is basically going to be equal to the half of the peripheral velocity of the blade here. Now we have to calculate the value of the degree of reaction. So again we have to calculate the degree of reaction here. So I have told you the degree of reaction is nothing but is the enthalpy change in the case of moving blade to the enthalpy change to the total blade here. So here in this in the case of compressor, axial flow compressor, the degree of reaction formula can be written as 1 minus VW2 divided by 2U2 here. Okay, so if you just put this condition here in this case, you will find the degree of reaction formula, the degree of reaction value will come out to be around 75% here. Okay, so that means option number B is going to be the correct answer of this question here. The next part, for a choked condition in a nozzle, choose the correct statement. See, now what is the meaning of choked flow here? Choked flow means the Mach number has been reached equal to 1 here, and the corresponding mass flow rate is equal to is going to be maximum here. Okay, so here we can see the Mach number at the throat is 1, that is correct here. The next part, the properties at the throat are called the critical properties, that is also correct, because in the case of choked condition we say the pressure, temperature and the velocity at the throat is known as the critical pressure, critical velocity as well as the critical temperature here. The next point is no more discharge is allowed even with the further decrease in exhaust pressure, that is also correct here. So here the option number D is going to be the correct answer of this question here. So that is a very basic questions here. The next part is energy conversion take place only one row of rotor of a nozzle blade, and later the steam glides over the rotor and the guide rows in the case of. Okay, So now just see, basically the answer of this question is the Curtis turbine here. Why Curtis turbine actually? Yeah, because in the case of whenever you cover the simple steam turbine here, see the D-level turbine is considered as a simple impulse turbine. But what happened actually, the speed of the D-level turbine is very high, okay, which is not suitable for producing the required frequency of electricity here. So in this case what we do the compounding of the steam turbine, and there are two ways of doing the compounding. The first one is the velocity compounding, and the second way is the pressure compounding. So in the case of pressure compounding, what we do, we expand the steam from the boiler pressure to the condenser pressure in a number of stages. So there we have a nozzle, then we have a moving blade, then we have a nozzle, then we have a moving blade. But in the case of Curtis turbine, or I can say in the case of velocity compounding turbine, what we do, we expand the velocity from higher to the lower velocity in a number of stages here, and the change in pressure, or I can say the drop in pressure is done in only one stage here. Okay, so that means the expansion of the steam from the boiler to condenser pressure is taking place in a single nozzle. After that we have a row of moving blade, fixed blade, moving blade, fixed blade here. Okay, and the velocity compounded turbine is known as the Curtis turbine. The pressure compounded turbine is known as the Raichu turbine, as well as the simple impulse turbine is known as the D-level turbine. Okay, so that is why the option number C is going to be D is going to be the correct answer here. And here the Parson turbine is nothing but it is a reaction turbine which is having a degree of reaction as 50% here. And here we have one more turbine which is known as the Heroes turbine here. And in the case of Heroes turbine, the degree of reaction is basically equal to 100% here. Okay, so you should have to remember the name of all of these turbines here. That is very important for you. Next part, Rankine efficiency of a steam power plant improves in summer as compared to that in winter, improves in winter as compared to that in the summer. And the next part is unaffected by the climate condition, none of the above. See, when we talk about the Rankine efficiency, the simple way of doing this question is like that. Just write down the efficiency formula of the Rankine cycle in terms of the mean temperature of heat rejection as well as the mean temperature of heat addition. So now just remember, in the case of Rankine cycle, the heat addition is taking place at the boiler. Okay, and the boiler is operating at the constant temperature no matter whatever the climatic conditions are. Okay, whether it is a summer condition or whether it is a cold winter season here. But if you see, whenever you are rejecting the heat from the condenser to the atmosphere, there you are going to see the variation in the mean temperature of heat rejection. Okay, so if you remember, in the case of winter season, the outside temperature or the atmospheric temperature, that is the mean temperature of heat rejection, is going to be very less as compared to the summer conditions. Okay, so we can say the efficiency in the winter is going to be more as compared to the efficiency in the summer condition here. Why so? Because in the summer the outside temperature is going to be more as compared to the outside temperature in the case of winter season here. Okay, so we can say the option number B is going to be the correct answer of this question here. Next part, if the enthalpy drop in a moving blade of a reaction turbine is 50 kJ per kg and in the case of fixed blade it is 100 kJ per kg, what will be the degree of reaction? So degree of reaction can be simply find out as 50 divided by 100 plus 50 here. So it will come out to be 33.33% here. So that means the answer B is going to be the correct answer here. Okay, option number B is going to be the next answer here. Next part, in a steam power plant, heat supplied to the boiler is 3600 kJ per kg and we have a cycle efficiency as 40%. You have to calculate the value of the steam rate. Now what is the meaning of steam rate here? See, steam rate simply means the amount of steam required to produce one net power output of 1 megawatt here, or I can say 1 kilowatt here. Okay, so here the steam rate, basically the steam rate can be written as mass flow rate of steam required to produce a net power output of 1 unity here. Okay, so here you can see, if I just simplify it further, it can be written in this way here. And if you want to find out in the unit of kilojoule per kilogram per kilowatt hour, what you have to do, you have to convert this second into the hour here, and correspondingly we can write the steam rate formula is going to be 3600 divided by network here. So that means to calculate the value of the steam rate, you need a value of the network here. So how do you calculate the network here? From the cycle efficiency. So cycle efficiency is nothing but it is equal to network divided by heat supplied. So we can say the net work is going to be equal to 0.4 multiplied by heat supplied, which is equal to 3600. Okay, so if you simplify it further, you can find your answer here. So here you can see the net work is coming out to be 1440 kilojoule per kg here. Okay, so just put this value in this formula and you will find out the value of the steam rate here. Okay, so if you solve this, you will get your answer here. So here the answer 2.5, around 2.5 is going to be the correct answer in this case here. Next point, gas turbines are used in aircraft. Now what is the main use, why do we prefer the gas turbine? Because in the case of aircraft, if you see, the weight has a major role here. Okay, we always ensure that the corresponding weight get reduced here. Okay, because it always create a problems. So in the case of a gas turbine, basically we are using the air, and air has a unique property that it is having a very low weight per unit power here. That is why we are preferring the gas turbine air in the case of gas turbine, or we can say that is why we are preferring the gas turbine in the case of aircraft and not the Rankine cycle here. Next part, thermal efficiency of a gas turbine cycle with intercooling. Now what is the effect of intercooling on the thermal efficiency of a gas turbine? Okay, so see, in this case again also you have to see the effect of mean temperature of heat addition as well as the mean temperature of heat rejection over the efficiency here. So now again I am writing the formula of the efficiency in terms of mean temperature of heat rejection divided by mean temperature of heat addition here. So let us suppose if you are just doing the intercooling here. So first of all, this red color cycle is representing this simple gas turbine cycle here. So if you perform the intercooling, it will be shown something like that, from 1 to 2 dash, then 3 dash, and then 4 dash here. So here you can see now what is the net effect over the efficiency here. Okay, so first of all, just see, due to the intercooling here, the mean temperature of heat addition is basically reducing here. It is basically reducing, and correspondingly if we talk about the effect of intercooling on the mean temperature of heat rejection, we are not sure whether the heat rejection is basically increasing or decreasing, because there is a very minor change here. Okay, due to these fluctuations here, so we can say it is almost less or same here. Okay, so I am not, it's the effect is very negligible here, or I can say negligible change here. Mean temperature of heat rejection can also get increased, it can also remain same, or it can also decreased here. Okay, it depends upon the intercooling conditions here. Okay, but the change with respect to mean temperature of heat addition is going to be less here. So here you can see the corresponding mean temperature of heat addition is basically decreasing. So correspondingly the efficiency is going to be decreased here, because the efficiency and a mean temperature of heat addition has a direct impact with each other. Okay, so we can say the option number B is going to be the correct answer. Okay, so here you can see the denominator is decreasing, that means this negative term is increasing here. So the final effect on the efficiency is going to decrease here. Next part, the gas turbine power plant operates on a Brayton cycle between the minimum temperature of 300 Kelvin and a maximum temperature of 1000 Kelvin here, and the maximum work done per kg of air will be. Okay, so here you have to calculate the value of the maximum work done. See, in the case of gas turbine cycle or a Brayton cycle, the formula of the maximum work done can be, the value of the maximum work done can be calculated by this formula here. Okay, so here you can see the value of Cp is given to you as 1 here, and the corresponding higher temperature is 1000 and the lower temperature is 300 here. Okay, so if you calculate this, you will find out the value of the maximum work here. So answer of this question is coming out to be around 204.5 here. That means the option number A is going to be the correct answer in this case. Option number A. Okay, the next part is, if the efficiency of a Brayton cycle and a Rankine cycle in a combined cycle are 20% and 30% respectively, then the efficiency of the combined cycle, we have to find out the efficiency of the combined cycle here. So always remember that whenever the two cycles are combined in series, then the combined efficiency can be written as 1 minus efficiency is equal to 1 minus efficiency 1 multiplied by 1 minus efficiency 2 here. Okay, or you can write it down as efficiency is going to be equal to efficiency of 1 plus efficiency of 2 minus efficiency 1 and 2 here. So just put out all the values and you will get your final answer. So here it will be the 0.2, 0.3 minus 0.2 multiplied by 0.3 here. Okay, so the answer is coming out to be around 0.44 here. Therefore, the efficiency of the combined cycle is going to be 44% here. Okay, so here we have covered the important 20 questions related to the power plant engineering. So here you can see all the questions which we have covered is basically majority of the questions are the theoretical ones and very less amount of numericals are there. Okay, so and the numerical questions are very simple. They have a direct concept here. You just have to use the direct formulas here. Okay, so in the case of BDL exam as well as the BEL exam, you can expect the numerical like this one here. Okay, so I hope you like this video here. Okay, so that is for today's video. So now we will meet in the next video here now. Okay, so thank you very much.